All right, let's talk about the brain, autism, and a scientific story that's been unfolding for decades. We're going to see how a really simple, powerful idea has evolved into something way more complex and honestly, way more interesting.
So, here's the big question to kick us off. For a long, long time, a lot of research was kind of hyper focused on finding one specific broken part in the brain that could explain the social challenges in autism. But what if that was the wrong way to look at it? What if the real issue isn't a single part at all, but a breakdown in communication across a massive, intricate network? To really get this, we have to start by meeting the main character of our story, a tiny but mighty part of the brain that's long been considered the absolute center of our social lives. And here it is, the amygdala. You can think of it as the brain's social surveillance system. It's constantly scanning, helping us read facial expressions, figure out if someone's trustworthy, and basically guiding our gut reactions in social situations. It is absolutely fundamental to how we navigate our world. So you can see why this idea, which came out way back in 2000, became so huge. It was called the amygdala theory of autism, and it was powerful. The thinking was, hey, if the amygdala is the social hub, then maybe issues right there could be the root cause of the social difficulties we see in autism. Let's break down the logic behind this theory for a second, because it's so clean and compelling. You'll see why it was the leading idea for so long. It just makes sense. So the thinking was basically this. Okay, step one, we know the amygdala handles social stuff. Step two, we know autism involves social challenges. So step three, connect the dots. Maybe, just maybe, an atypical amygdala is the core reason. It's an elegant, simple, A plus B equals C kind of hypothesis. But here's the thing about a really neat, clean theory. You gotta test it in the real world. So scientists came up with a pretty brilliant way to put this idea under the microscope. And, well, this is where the picture starts to get a lot more complicated. And here's the clever part. The setup was this. If the amygdala theory is right, then people with autism should behave in very similar ways to people who have very specific, isolated damage only to their amygdalas and nowhere else. It's a perfect head-to-head comparison. Okay, now look at this, because this is where it gets fascinating. For some things, like face perception or judging trustworthiness, the theory holds up. Both groups show similar atypical patterns. But then, you get to social attention. And whoa. Individuals with autism had a less efficient visual search for faces, but the patients with amygdala damage, they performed normally. Right there, in that one row, the whole theory starts to crack. And that is a huge deal. It was a stunning finding, really. It tells us that while the amygdala is definitely involved, it's clearly a player, damage to it all by itself just doesn't create the full picture of autism. Our neat and tidy broken part theory, well, it had to be incomplete. There's something more going on. And that something more has pushed researchers to totally change their perspective, to zoom out, to stop looking at a single instrument in the orchestra and start listening to how the entire orchestra plays together. This is where the story shifts from brain regions to brain networks. I love this analogy. The new thinking is like this. The problem isn't a single broken drum, that's the amygdala. The problem is a communication issue across the whole orchestra. It's about how the amygdala talks to other key areas, like the prefrontal cortex, the orchestra's conductor. It's about timing and coordination between all the different sections. So how do you even measure this crosstalk? Well, scientists use a concept called functional connectivity. It's basically a way to map out which parts of the brain are firing in sync with each other over time. It shows us how well different areas are coordinating, how they're working together as a team. And right now, this is where the really exciting debate is. There are two big ideas on the table. One is underconnectivity, the idea that maybe the long-range connections between distant brain regions are weaker. The other is overconnectivity, the idea that maybe the local short-range connections are too strong, creating a lot of background noise. And what's really wild is that it might actually be both happening at the same time. So mapping all this stuff sounds incredibly complex, right? How in the world are scientists actually charting these brain networks today? Well, they have a whole new generation of incredibly powerful tools in their toolkit. I mean, we are talking about next level stuff. They're combining different kinds of brain scans to get a complete picture of both structure and activity. They're using AI and machine learning to find patterns in the data that no human could ever spot. And in some really rare opportunities, they can even record from single individual neurons in human patients. This is how we're starting to see the brain's dynamic conversation in ways we could only dream of a decade ago. And that leaves us with this final crucial question. This huge shift from looking for a broken part to studying a breakdown in communication, it isn't just changing how we study autism. It's changing how we understand the brain, period. It suggests that for so many complex conditions, the answer might not be in one spot, but in the connections that link everything together. And that right there opens